Welcome back. We're going to be looking at axial members and introduction to shape functions. And again, we'll talk about shape functions and what they are as we move through the presentation. But just want to highlight the next group presentation will be examining the general loading of structural members, so things that are static, and machine components, things that are dynamically moving, but specifically looking at the push-pull and the bending of those machine components. So that's where we're headed. We'll do a look at some of that today, but not all of it. First aspect of that. Torsion, by the way, we'll examine that later, further on down the line. If you're wondering where that is in the next 3 lectures, it'll be coming up. All right, so let's go look into this and see what we got. So if we look at linear elements, we consider we have linear elements in axial loading. An example here is if we have a couple different floors and some vertical members supporting these different floors, let's call them. And we can assume central axial loading. There's no bending here. It's hopefully not going from side to side, just straight up and down. We could load it like this. So we have different forces that the different floors are applying on this column. So force at node 4, at node 3, node 2, and nothing at node 1 besides the weight of the column. And then we have different elements between those things, 1, 2, and 3. All right. So how can we look at this? All right, let's develop an individual axial elements, so again, one element at a time. So they'll have nodes I and j as normal. And at least in this particular orientation, we have, they're in the global y, yi and yj. So it's the global locations of those nodes. There's going to be nodal deflections at both those nodes, and those will be represented by the capital U. And then there's the length that we have between those two nodes, and that length is equal to the difference in the y components at node j and node I. So we can actually determine what that L value is. All right, so let's solve for some unknown deflection. If we actually want to figure out what the deflection is between some nodes, let's see how we can figure that out. If we assume a linear deflection distribution, so it's linear, keyword there, right? So straight line, if it's linear, then we have to have the form of y equals mx plus b. Let's see what we get here. So y in our case is going to be the deflection, u. X is going to be our y, so where are we at in the element is what y is telling us. And then we have C2 is essentially our slope, and B is our y-intercept. Right, so that's we're maintaining that form here. All right. So the deflection, again, it's the deflection at any point y within the element. So this is any point within the element, between nodes I and j of our element. All right, so with two unknown in the equation, we've got C1 with C2. We need two equations. So two equations, two unknowns. Or two unknowns, two equations, I guess say in the reverse there. So we're going to say we have some deflection U equals UI at this location Y equals YI. So at node I, we have this deflection. So here's YI, we substitute in there when we have the deflection there at node I. All right. Again, the deflection we have is some deflection at J is at that location. So we're substituting location Y sub J and the deflection that occurs at that point, at that node. All right, so there are two equations. So we can solve simultaneously and get what C1 is equal to and C2. So we got our two constants. Now we can plug those back in to our original equation for the displacement. So now, if we know the location of our two nodes, so here's node J and here's node I, etc., etc., then we can put in some location between those two, and we can solve for what that deflection is. Right, that's pretty neat. So again, C1 is our y-intercept. Right, so here's mx plus b. This is b right here. And mx, here's x, and this is m. So m is the slope. So C2 is our slope, and C1 is our y-intercept. All right, so let's rearrange this equation, the equation we had on the previous slide. And we're now going to solve it in terms of ui and uj. So here's the first equation. We're going to break that out into ui and uj. And the second equation, the slope, as it were, we're going to break that out into uj and ui again. All right, now let's collect those terms. So we're going to collect all the terms that have ui in them, right here and right here. So we're going to collect those terms, and this becomes this equation. And do the same thing for uj. And we're going to define the terms in the parentheses here. So this term here is Si, and this term here is Sj. S sub j. All right, and these are very, very key things going forward. All right. The SI and SJ are called our shape functions. They literally describe the shape or the deflection of each element. We use these shape functions to figure out what the deflection is at any point between two nodes. Hence the name shape functions. All right. So if we know what L is, back from the with the first slide where we defined our problem, our length of our element is defined by the difference between the y components at each node. And we can substitute that into the denominator and come up with our shape functions. For node I is yj minus y over L. And for the shape function at node j is y minus yi over L. All right, so therefore, if we plug the shape functions back into our original equation, we can now have the shape functions, so si times ui and sj times uj. All right, so this is happening, what stuff is happening in node I and stuff happening in node j, and that defines what the deflection is in our element. All right, so again, I'm just kind of rehash this many times. This is the deflection at any point within the element. So the u and the u superscript either is the deflection at any point within our element. So in matrix form, if we wanted to write this, we could take our shape function in node I, shape function in node j. So this is kind of a row matrix, and then we have our deflections here. Not really clear here. There should be a space between these two, but just FYI. But if we take this row, multiply times this column, we basically recreate this equation up here. All right, the same approach can be used to approximate the variation of any unknown variable, such as temperature and velocity. So we can come back, and we'll be doing this later, but we'll substitute in, instead of using displacement, we'll use temperature. And we'll have temperatures over here. So knowing these two temperatures at two different ends of our element, we can solve for the temperature within the element. All right, so we'll come back to that. All right, so let's look at the local coordinate system. So we notice that y starts at node I. So here's y. So here's our local coordinate system. This is, again, over here. This is the global system for y. So if that's the case, capital Y, right, the location any point within our element is equal to y sub I plus y will give us any point within our element. So that's where that comes from. So that describes that. We can substitute that now into our shape function. So here's the original shape function with the length of our element. So substituting into, for the y variable, the location any point within our element, we're going to substitute in our function up here that we just derived. All right, solving for, we're going to bring the two global coordinates together. Ooh, what does that look like? Y sub j minus y sub I, that's the same as this guy right here. That's the length. So let's substitute in that, and we get L minus y over L. Let's do the same thing for the shape function node j. So we'll start off substituting for a y here. There's the substitution. We're going to collect terms here. This is a positive. This one's minus yi. That means they go away. All right, so we're left with, let me do that a little bit faster. So this is going to be, that's going to go to 0. All right, so we got the shape function node I, 1 minus y over L. So just kind of rearranging there again. And Sj is equal to y over L. All right, so notice that y, it goes from 0 to L. Anything beyond that doesn't really make sense. So y is somewhere between 0 and L, which is good because that's what we're wanting for a local coordinate system. And also see that if we're at node I, so when we're at node I, y is equal to 0 at node I. So if we plug in 0 here, we get 1 minus 0, and that just gives us 1. So the shape function is 1 at node I, and the shape function for node I, right, is 0 at node j. So if we plug in y equal to L up here, so we get 1 minus L over L, that's 1, so 1 minus 1 is 0. So we get the shape function 1 at its own node, and that same shape function is 0 at the other node. Right. Likewise, shape function node j is 0 at node I, but the shape function for node j is 1 at node j. So notice those different ones. When it's at its own node, it's 1. When it's at another node, or at least at node I, it's 0. This is a key property of our shape functions.